Okay, well, let's give this a run, see how it goes. Today's lecture is on the first part of nuclear chemistry. We're actually going to do two talks on nuclear chemistry. The reason I have to see how it works is I'm going to have to try to use the blackboard a little bit. And so I'm going to have to try to turn, whenever I have to use the blackboard, I'm going to have to turn the camera, and hopefully I'll be able to focus the camera on the blackboard so that you can see what I'm doing. So today's talk, as I said, is on nuclear chemistry, which is the, well, let me go on to the next slide and we'll define nuclear chemistry. Nuclear chemistry is the study of reactions that involve changes in the nuclear structure. So in all of the other stuff that we've been doing, essentially the nuclear structure of the various atoms and molecules that we've been dealing with has remained intact. But now we're going to look at specific types of reactions that cause a change in the actual nuclei. And so elements are actually going to change their identity based on what happens. A nucleide is a single type of nucleus that participates in a nuclear reaction. Nucleons is just a more generic name for the parts of the nucleus, specifically the protons and neutrons. Now, when you express a element, you express it with three values. The large X here represents the symbol that's on the periodic table for that element. The A, which is a superscript, represents the atomic mass for that element, and the Z, or subscript, is the atomic number. Now, if you recall, the atomic number is the number of protons, and the atomic number is what determines the identity of the element. So, for example, all elements with the atomic number of 1 are hydrogen. The atomic mass does not determine the identity, only the atomic number, which determines the number of protons, number of electrons. So when we write, say, iodine 131, we're writing 131 up here in the A position. That's the atomic mass for that compound, and not the atomic number. Isotopes, if you recall, are elements that have the same atomic number but different atomic masses. Now, the nucleons, the protons and neutrons, are held together by something called a strong nuclear force. These are forces of attraction that hold together the nucleus and allow the nucleus to hold together. Now, this is also sometimes called the nuclear binding energy, and this energy comes from something called the mass defect. Oops, sorry. So, for example, over here we have four nucleons, 2 protons and 2 electrons. We look at the individual weights of each proton and each neutron, and you sum those up and you get a number. You then weigh the mass of the whole nucleus, you get a separate number. Those two numbers are not exactly the same, and the difference between those two numbers is called the mass defect. And you will find that this mass of the nucleus is always slightly less than the mass of the nucleon, the individual nucleons. This adds up. This difference is then translated into an energy, which I'll show you how to do that in just a minute. And that represents the strong nuclear force or the binding energy. This shows you the same thing. You have 4 hydrogen atoms over here, and then you look at the helium, which is bound together. These have no binding energy to each other. These, on the other hand, have a binding energy, and because of the mass defect that's present here, but not here, the weight here is greater than the mass here. Now, because of this greater mass, this difference in masses is converted into an energy that holds the nucleus together, and that is called the nuclear binding energy. This is the energy that's produced when the atom's nucleons are bound together. This is also the energy that's needed to break apart the nucleus into its constituent protons and neutrons. So the binding energy is that energy that holds together the nucleons in the nucleus, and it's the energy that would be required if you wanted to break apart the various nucleons. And this is calculated by finding the mass defect and converting that into an energy value. So the mass energy, this is done by using what's called the mass energy equivalence equation, which everybody knows because they have seen it on television or seen it on something they've read about Einstein. It was developed by Albert Einstein, and it's a way of converting the mass of nuclear particles into energy. And that energy is equal to the mass times the square of the speed of light. So the energy equivalent of mass is a very large number. And it turns out that this mass defect is what constitutes the binding energy that holds the nucleus together. So let's take a look at some problems. Calculate the mass defect for an isotope of 206 lead. The mass of 206 lead is 205.97444 AMU. The mass of the proton is given there as 1.00728, and the mass of the neutron is 1.00866. Now, in order to do this, we have to look up on the periodic table, we have to look up the atomic number so that we can find the number of neutrons and the number of protons. So that's what I'm doing right now is I pulled a book out and I'm looking up lead to see what the atomic number is for lead. I probably should have had this out already, but I'll live. Let's see if I can find this. You can probably hear the book rattling around over the microphone. Here we go. So lead has an atomic number of 82. So what we would do, let me see if I can move this camera over so it'll take a picture of the blackboard. Make sure I am taking a picture of the blackboard. Yep, looks like I am. Okay. Okay, so we have, not wearing a tie if I'm doing this, we have 82 protons times 1.00728 and 205 minus 82 is 123 neutrons times 1.00866, and we get numbers for that. Let me do this real quick over here. My phone is what I use to do the taping, so I don't have a calculator. Now you have to do this out to several digits because these differences are fairly small. So this comes out to 82.59696. Then we take the 123 and multiply that by 1.00866. 18, one's 19, one's 25, 3, 12, 13, one's 17, make sure I did that right. I may not have. Oh, this is, shoot, do this again. There's a 0 here, and then we do it. So 2 times 2 times that's 12, 13, 17, 0, 2, 2 zeros here, and then you just 6, 6, 8, 0, 0, 1, add all that up and you get 8, 1, 5, 1 here is 6, 1 here is 0, 1 here is 4, 2, 1. So that's 124.06518. You add all this up, you get 14, 1, 2, 6, 5, or 6, excuse me, .602. So that's the mass based on the individual components. If you subtract 205.97444, you have a mass deficit of 0.68770. And then you plug that into this equation, c squared, where c is 3 times 10 to the minus 8, or plus 8, excuse me. And so if you do that calculation, you end up with the answer to this problem. Now hopefully this has come out so that you can see it, but I'm going to hold it up here and make sure you can see it. On the left, you see where I've calculated the individual, and then on the right, I've added those together. And I'm not swearing that I didn't make a mathematical mistake here, but hopefully I didn't. And you ultimately have a mass deficit of 0.68770, which multiplied by the square of the speed of light gives you the energy in joules. Okie dokie. So let me move this back over on this side. Now, there's a second problem here, which I'm not going to do right now. Which is shown right here. The net reaction for fusion on a star like the Sun is 4 hydrogen goes to form 1 helium plus 2 electrons. Again, using the same calculations, you can calculate the mass deficit. And with a calculator, it's a whole lot easier. Unfortunately, my phone is my video camera, so I'm not able to use a calculator here. Now, let's talk about nuclear stability. A nucleus is considered stable if it cannot be transformed into another configuration without the addition of energy from the outside. And so a nucleus is considered stable when it will sit in an environment and there's no outside interaction, and it will remain as it is. It's unstable if it will decompose or change without the addition of outside energy. Now there's something known as the band of stability, and that's what's shown on this slide. If you look at, on this part of the slide is the number of protons in the nucleus. Here is the number of neutrons. And the band of stability is after you make a plot of the number of protons versus the number of neutrons. It's this very small area that if your atom falls into this area, it will be stable. If your atom falls outside this area in the green part, the wider part, then it is unstable and radioactive. And then outside that is unreality. Nothing exists outside of that. And so this little area right here, this sort of purple-blue area, very narrow line, is called the band of stability. So if you're looking at something, you want to know if it's stable or not, you do this, you look at a plot like this and see where it falls, and if it falls on the blue line, it's considered stable, otherwise it's unstable. So as I said, this plot shows the nuclides that are known to exist and those that are stable. The stable nuclides are indicated in blue, the unstable are indicated in green. Note that all isotopes of elements with atomic numbers greater than 83, so above this point right here, those are all unstable. A solid line is where the number of neutrons and the number of protons are equal. So you see that very quickly as they get larger and larger, you get more and more neutrons compared to the number of protons. And so that's why it shifts toward the left of the straight line. Now when a atom or nuclei is unstable, it's generally either to the left or to the right of the band of stability. So it's either to the left or to the right of the band of stability. The magic number is the number of nucleons in a particular nuclei that is associated with stability. So it's the number of nucleons in a particular element that's necessary for stability. So each element, like iron or lead or whatever, has a magic number, which is the number of each nucleon that's necessary to make it stable. And then all other nucleon combinations in that element are unstable. And you can also calculate the binding energy per nucleon. So for example, in the previous calculation we did, we had 206 nucleons. So if we divided the energy that we found by the number of nucleons, we could come up with a number that would represent the binding energy per nucleon. And you see that you can plot the mass number. For example, here's 206, and you can plot a binding energy per nucleon. And if you where you fall on this line, determines whether your molecule will break apart or undergo fission, or will come together and undergo fusion. So you notice that radioactive lead, for example, would undergo fission. It's over here. And a fusion reaction would be something like two hydrogens coming together. The largest number is in this band right here. And it, as it says here, it represents approximately 56 nucleons. It's actually right in this area right here. So let's take a look at a couple more problems. We calculate the mass defect, binding energy, and binding energy per nucleon for the following isotopes. Now this is just practice. I may pick one of these to do myself. Well, there's two of them here. And because it's easier, I'm going to do the easier one and then show you on the board here. It's the same kind of calculation you just did previously. I'll talk it through first and then I'll show you with the camera after that. So N14, nitrogen 14, has 7 protons and 7 neutrons. And so we see that the mass of the proton, and I actually don't take into account the mass of electron, but you can do that if you want. So for example, the mass of a proton is 1.6726231. The mass of a neutron is 674, 9286. Okay? The AMU mass for the total would be 1.6605, 402. So you would multiply that by 14. So we'll do that in just a second. So let's we'll take 7 times the first one here. If we do that, we get 7, 21, 16. I'll show you in just a second what we're getting to. 2, 18, 50, 7. Of course, you've got your calculator, so you got it easier than I do. And then we take 7 times 1.674928.6 times 7 is 42. 56 is 60. 20, 65, 28 plus 6 is 34, 52, 47. So we have 11.7082 617 and 11.7245002. We add those two together and we get 9167223. 3, 4, 23. So we get 23.4327619. If we take 14 times our 1.6605,402, we're going to get 8, 2, 6, 5, 7, 4, 2, 3, 2. So we're going to subtract 23.24, 75, 628. Okay, let me show you. Let me get the camera and show you what I've done here. Okay, so you can see we have 7 protons and 7 neutrons. And then right below there, I've done the calculation for the mass of each of those. One's 11.708 and change, the other's 11.724. And I put those two numbers up there and added them together. Then I took 14 times this other number and got this number, which I put underneath it. And then you subtract and you see there's going to be a small difference, which is the mass defect. You then take that mass defect and plug it into the E equals mc squared, where m will be the difference between those two numbers and c is the speed of light. And once you get that number, you then divide that by 14, which is the number of nucleons you have, and that gives you the binding energy per nucleon. If you don't understand this, we can do some of these at the help session later on. Okay, let's talk about nuclear equations. First of all, you have to know some of the nuclear particles, and this table reviews the nuclear particles that we generally talk about. The top particle is the alpha particle. It represents a helium nucleus. It's a high energy, has a lot of mass, not a very deep penetration. The beta particle is an electron. The symbols are here. It is high energy, but has a lower mass, so it penetrates a greater distance because it's less damage. A positron is a positively charged electron, has the same mass as an electron, but it has a positive charge. A proton is a single proton or the nucleus of a hydrogen atom. Neutron is a neutron. And then lastly are the very high energy electromagnetic waves called gamma rays. Now when you do equations, nuclear equations, there are certain rules that you have to follow. One rule is that the sum of the mass numbers of the reactants must equal the sum of the mass numbers of the products. Matter can neither be created nor destroyed, so whatever you start out with is what you have to finish with. The sum of the charges of the reactants must equal the sum of the charges of the products. Again, you cannot create or destroy charge. The atomic number, or Z, determines the identity of the element. So you use the periodic table. If, for example, you know the atomic number, but you're not sure what element it is, you look on the periodic table, the atomic number will tell you what the element is. So here are some examples. Here's a couple of examples. Here you have U, 2 235, 92, U is the symbol for uranium, plus 1 neutron. Now when you look at the mass conservation, you have 235 plus 1, so you have 236 on this side. This forms cesium 138 plus rubidium 96 plus 2 neutrons. So 138 plus 96 plus 2 has to equal this. So this is 236. This is 234 plus 2 is 236. So the nuclear charge, or the atomic number, also has to be conserved. So 92 plus 0 has to equal 55 plus 37 plus 2 zeros. 55 plus 37 is 92, and that's 92. So that's an example of how you have to put together a nuclear equation. So here are some quiz questions or some examples. You have Pu 242 94 goes to form He 4 over 2 plus what? So the top, this by itself has to equal 4 plus something. So if you subtract 4 from 242, you get 238. So the atomic mass here has to be 238. Again, 94 has to equal 2 plus something. So it's going to be 238 and 92. 92 plus 2 equals 94. 238 plus 4 is equal to 242. Now if you look up 92 on your periodic table, you'll see that 92, I believe it's U, but let me look and make sure. Yes. So the answer, or the fill in the blank in this first one here, is U 238 92. Here's another one. Something over here is going to equal all of this. Mass-wise, it's going to be 32 plus 0, so it's going to be atomic mass of 32. Charge-wise, it's going to be 16 plus a minus 1, or 15. So it's going to be 32, 15. If we look in the periodic table, the atomic number of 15 is phosphorus. So it's going to be P 32, 15. Now you have to do some of these practice-wise because this will be on the quiz. I will do one of these types of problems, just like there's a good chance that we will do a mass defect problem as the problems on the quiz. So make sure to try these other three for your own practice, but that's how you do it to fill in these blanks. Okay, let's talk about the various types of radioactive decay. Radioactive decay is when you have an unstable nucleus. It's a spontaneous change in that unstable nucleus. The reactant of that unstable nuclide is called the parent nuclide. The product of that is called the daughter nuclei. So in this case, uranium is the parent nuclei and thorium is the daughter nuclei. So a nucleus of uranium-238 undergoes an alpha decay with the production of an alpha particle, so this is called an alpha decay, to form thorium-234. The alpha particle removes 2 protons and 2 neutrons in the process. So uranium-238 has an atomic number of 92. That atomic number drops 2 parts so that thorium-234 has an atomic number of 90, which is why it's thorium. Alpha particles are attracted, because of their positive charge, they're attracted by a negative shield or plate. Conversely, beta particles, which are electrons and therefore are negative, are attracted by a positively charged plate. Gamma, which is electromagnetic radiation having no charge, is unaffected by electrical charge. So you see on this diagram, a radioactive substance that emits more than one type of particle, they can be separated using charged plates, which will cause the positives to go deflect downward because of the effect of the negative plate. The negatives deflect upward, and also notice that the upward deflection is greater than the downward deflection, and that's because the beta particles are lighter and smaller and can be deflected more by the same amount of force. And notice the gamma rays are totally unaffected. Now, in addition to the alpha decay, which we just mentioned with the production of an alpha particle, we also have beta decay, which is the production of a beta particle, gamma decay with the production of gamma rays, what's called positron emission, which is the production of a single proton, and electron capture, which is where an electron moves in and is captured by the nucleus. What you notice is the A will be decreased by 4 and the Z by 2 when you lose the alpha particle. The A is unchanged because the electron has no mass, comparative relative mass, and the Z actually increases because it has a negative charge. There's no change in either of these with gamma radiation. The A is unchanged and the Z decreases by 1 if you have positron emission. And then in electron capture, A is unchanged and Z decreases by 1. Now, this shows the way you can use one type of radioactive decay. A PET scanner, and PET stands for positron emission tomography. So what happens here is you take this oxygen and you add a positron. So it's positron emission. It forms fluorine and a neutron. And this, depending on how much metabolic activity is occurring in this brain, it leads to a change or an imaging that you can pick up. So on this side you have a brain that's very active, a normal brain, and then you have a brain that's much less active, and it's a brain of a patient with Alzheimer's disease. We're going to talk quite a bit more the next lecture on uses of radioactive materials. Now, radioactive decay can occur more than once. In other words, sometimes it doesn't stop with a single decay. And when it goes through an entire series of reactions, it's called a radioactive decay series. This is a natural occurring decay that occurs starting at the heaviest element, and it falls through a series of successive degradations or integrations and decays and ends up until it reaches a stable finding. And what you see here is you start with uranium, and each of this direction is an alpha decay, and each of the back direction is a beta decay. And so it starts here, alpha decay, beta decay, alpha, 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 beta, beta, alpha, beta, beta, until you reach lead. And those several steps represent a series. And that's what it shows here. Uranium-238 undergoes a radioactive decay series, and there is actually 14 separate steps until it reaches stable lead-206. This series consists of, these 14 steps include 8 alpha steps and 6 beta steps. Now let's talk about half-lives. We've talked about this before, but let's review this. A half-life is the time required for half of an atom's material to decay. So if you start out with 10 grams of cobalt-60, if the half-life is 5.27 years, then after 5.27 years, you have half as much. After another 5.27 years, you have half of that, and half of that. Now, you'll recall in the equation on, or in the chapter on rates of reaction, that you can express half-lives this way. This is the degradation constant or decay constant. The decay constant, or K, is equal to ln2 over T1 half, or 0.693 over the half-life, so that the half-life is equal to the log of 2 divided by the decay constant. Now in this chapter, we're calling it gamma. In the previous chapter, the degradation constant was called lowercase k. So if you start with a certain amount of material, N0, and you want to know how much you have after a certain time, you take N0 times e to the kt, or gamma t, where gamma, or k, is equal to the decay constant. In this case, the decay constant would be 5.27. And this can be simplified so that t, that is the time it takes to get a certain amount, a certain ratio, is equal to 1 over the constant times the natural log of the total the amount after t divided by the original amount. Let's say, for example, you wanted to know how much you have, how long it would take to have 1% of the material left. Then this ratio would be 1 over 100, and then you would know gamma. You would put those in here and solve for t, and it would tell you how much that is. So for cobalt 60, 50%, 1 over 2, remains after 5.27 years, 25% after 10.54, and so on. Now here are some problems, and I don't have a calculator to do natural logs, so I'm not going to be able to do these for you, but we can do these at the help session. But these are the kind of problems that might be on a quiz or test. Palladium 100 has a half-life of 3.6 days. If you start with 1 mole of atoms, that's 6.022 times 10 to the 23rd, how many would you have after 20 days? Okay, you can use that previous formula, this formula, to find that. Okay, and K in this case would be 3.6 days. Here's another problem. How long will it take for 40 grams of material? And it gives the half-life, so you can use the half-life to find K to decay to 1% of its original. And I told you that, that's a ratio of 1 over 100. So we'll do this at the help session. I'm just not confident that working on the board here is working real well right now. So we're going to finish up with a couple of slides on radioactive dating. And I don't mean guys and girls going out to the movies. Radioactive dating is, or radiometric dating, is using isotopes to determine the age of things that are very old, archaeological artifacts. Radiocarbon dating is radiometric dating using carbon-14 in order to date objects. So this explains what they do. So you have both stable carbon-12 and radioactive carbon-14, and that's shown up here. So you have trace amounts of radioactive carbon-14, about 1% of carbon-13, and most carbon-12, okay? This is caused by the destruction of nitrogen. Now, all of these carbons are taken in by plants and animals and remain at a constant level while they're alive. Now, that's an assumption that they remain at a constant level while they're alive. After death, the C14 will decay. The reason they say it's a constant level is they assume that the exposure here is constant, and therefore, if he eats the same amount over a long period of time, it will remain constant throughout. Okay, so the ratio is constant while they're living. The ratio of 12 to 14 is constant while they're living. But once they die, there's no more uptake of from the environment because they die, so the decay begins, and the carbon-14 decay begins. And so as carbon-14 degenerates, the ratio of 14 to 12 decreases. And so by comparing the ratio in living to the ratio of deceased, you can tell how long the organism was dead, lived and died, how long ago it was alive. So that's how carbon dating works. Now, carbon dating is also used to determine the age of documents because these are made from trees, and you'll notice that back here, trees also take up carbon, both carbon-12 and carbon-14, and once the tree's cut down, the 14 begins to degenerate and the 12 stays constant. And so, again, you can use that to date something like these scrolls. So I'm going to finish at this point, and actually, since I'm done, I may go back to this problem right here and see if I can do this on the board for you. Let me erase what's already on here, and I may try to see if I can put the formulas up here so you can see them while we're working on it. We've got a couple of minutes here. So we know that the half-life is 3.60 days. And I am going to reach a problem because I can't do natural laws. And you're starting with 6.023 times 10 to the 23rd. So that's N0. And what you want to know is NT after a time period T of 20 days. So I wrote down the necessary numbers, so let me back the slide up so we can see, whoops, I'm going the wrong way here. So here, the formula we're gonna need is either, you can use this formula here, or well, either one of these two formulas, and you can use this to determine gamma, okay? You can take the half-life, okay, and put that in here. So let me see if I can set this up so we can, so I can show you how to do it. So let me point this at the board and see if I can pull this off. Okay, you can see the numbers up here. So first of all, you can say that gamma equals 0.693, which is the log of 2 over the half-life, which is 3.60 days. And so gamma is going to be that. And once you get that number, the next line down, we already know T, so what we want to know is NT. So NT equals N0 E to the minus gamma T. So NT is going to be 6.02 times 3 times 10 to the 23rd times E to the minus gamma times 20, and the gamma is what you get over on this side. So you take the answer you get for this calculation and put it into that equation, and that should give you the answer for that. I want to thank you for your attention, and hopefully this worked out. I'm a little bit worried about Let me move this in to make sure you can see exactly what we're talking about here. I'm a little bit worried about working on the board here, but other than that, I think we're good. We have 3 possible quiz questions here. We could do a quiz question like the one I'm showing you right here. We could do a quiz question like showing mass defect and binding energy. And we could do a quiz question with the nuclear equations. Thank you very much.